Hi, I'm Frank Gupton. I'm the chair of the Chemical Life Science Engineering Department at the VCU College of Engineering. And my work is in a fairly broad area of chemical engineering. The lab that you're in right now is our catalysis lab. It's funded by the National Science Foundation. And we've developed all kinds of new catalysts that can be used to make pharmaceutical products. And as part of that, it's a part of a bigger effort on our part to increase access to global health care. We also have major grants with the Bill and Melinda Gates Foundation to work on reducing the cost and increasing the access of HIV drugs on a global basis, but specifically on the African continent. The other area that we're working on is related to COVID-19. We've developed new processes for remdesivir and other drugs associated with treatment of COVID-19. We also are working in an area in collaboration with a new corporation that's been formed in Richmond called Flow Corporation. And what we're working on is bringing pharmaceutical manufacturing back to the United States so that we can make our own drugs, and we're not dependent upon foreign entities to supply materials. And that kind of gives you a broader perspective on what we're doing, but really what it boils down to is solving problems, and that's what engineers do best. I think that's one of the reasons why our students are so well versed and can work in a lot of different areas, because they all know how to solve problems, no matter what the problem is, whether it's catalysis or global healthcare or fixing our U.S. broken supply chain. It's all about fixing problems. And I think that's one of the great things about engineering, that's a common thread that goes between all the different disciplines that we have here, that we're all problem solvers and working on things that are hopefully going to get out in the marketplace and improve the quality of life for people in the United States and around the world. So over here we've got one of our reactors that we use to make our catalyst. And this is just a fancy version of a microwave oven like you might have in your kitchen. What this does, though, it allows us to adjust the power levels that you couldn't get on a microwave oven in your kitchen. And what we do is we deposit metal nanoparticles onto support systems, and then we fix them by nuking them with the microwave. And what happens is that a microwave works on the principle of heating up materials that are real polar, like water. And when you use a microwave, what you're really heating up is the water inside the food, because it's absorbing all of the energy. And metals are even more polar than water, and that's why when you put a metal pan into a microwave, it starts to arc. So what we do is we deposit metal nanoparticles onto a support system, then we put them in the microwave, and what happens is that the microwave energy is selectively absorbed by these little metal nanoparticles, and they heat up to about 300 or 400 degrees centigrade, and then they burn a hole into the support system, and it fixes them. And what the catalysts that we've developed not only are immobilized onto these supports, but we've picked a support called graphene. And graphene is two-dimensional carbon, and it's a great semiconductor. So what happens is that the graphene actually accelerates the catalytic reactions by shunting electrons back and forth between the metal nanoparticles. And a reaction that normally takes maybe about 8 to 10 hours now, we can do in about 30 seconds. And by doing that, we've set ourselves up to be able to use new manufacturing platforms that would allow us to produce drugs and other materials more efficiently. So once we've made the catalysts, what we'll do is we'll put them into a catalyst bed, and these are all different catalyst beds, so we can look at multiple catalysts in parallel. And we have a sampling system that's built into this, so we can program the catalyst beds based on temperature, flow rate, and pressure. And this unit here will actually allow us to sample the product coming out of here in real time and archive all of that data as far as our ability to make product or convert the starting materials into product. And then it's all automated so that we just turn it on in the evenings, walk away, and in the morning you come back and you've got all your data ready to go. So that's the beginning of the process with regards to how to make the catalyst. And everything that we do, all of our students understand that everything that we do here has to be scalable to commercial operations. They can't just be laboratory curiosities. So the methods that we use to make the catalyst and the applications that we're using the catalyst in all are scalable to commercial operations. And we planned on having these catalysts being used by most of the major pharmaceutical companies.